Hi class, today we'll be looking at section 8.6. This first video will introduce the two concepts we need to be able to understand for this lesson, and the second video will just show a bunch of examples and practice. So our objective today is that I can solve a quadratic equation in vertex form, graphically, or algebraically. So the good news about this is if you understood solving absolute value equations graphically and algebraically, and if you understood graphing parabolas review yesterday, you should be pretty good to go for today. So if we're asked to solve vertex form equations, we're going to do what we did with absolute value, where we're going to graph both sides of the equation. So in the first one, I'm going to draw that horizontal line first at y equals 1. And then the second thing I'm going to do is on the graph the other side of the equation, 2 times x minus 3 squared minus 7, which is review of what we did yesterday. First I need to find the vertex. I have an x minus 3 squared, so I'm going to do a positive 3, and then the minus 7 on the end says it's at 3, negative 7. So I go over 3, down 7, and I plot my point. Now remember, at a minimum, we need 5 points to graph a vertex. Oops, sorry, this is supposed to be up here. So from the vertex, I'm going to go over 1, up a times 1 squared. My a in this case is 2. Is that 2 in front of the absolute value? So I'm going to do 2 times 1 squared, and I get 2, which means I go over 2, over 1, sorry, up 2. So from the vertex, over 1, up 2, over 1, up 2. And then from the vertex, I'm going to go over 2, up a times 4. Now we've been talking about this as 2 squared. So I'm going to do a times 2 squared virtually, which the a is 2, times 2 squared is 4, and so I go 8. So I go over 2, up 8. So again, this is what we reviewed in yesterday's lesson. Over 2, up 8, and it actually puts me on that line, which is what I'm going for. Again, I do need to keep plotting points until I hit that horizontal line. Once I do, I am sufficient with my points, and I can draw the parabola through it. But there will be times where you actually have to plot more than your 5 points because you do need it to go through that line, and we'll talk about that in the next example. So once I have my graph drawn with exact points where they intersect, this is the point 1, 1, and this is the point 5, 1. Remember, the points of intersection are not the answers, but rather it is the x values of those points of intersection. So my answer is x equals 1 or x equals 5 in this example. Now the next question is, what's it going to look like if it has no solutions? Very similar to what we talked about with the absolute value. The way this would have no solutions would be if this horizontal line was below the parabola in this case, so it never crossed it. And the way it would be one solution would be if the horizontal line went right through the vertex. So just like with absolute values, you could end up with 2 solutions, 1 solution, or 0 solutions when you are solving a quadratic equation graphically, or algebraically for that matter. Okay, so this next example, I want you to try to at least set it up, meaning I want you to graph the horizontal line and graph your first 5 points of the quadratic. At that point, you might get stumped, and then you can start playing the video. Otherwise, if you want to extend your learning and try to figure it out on your own and then check it, that would be great as well. So pause the video and see what you can do. Again, the first thing I did here is I graphed y equals negative 2. So horizontal line at negative 2. And then I needed to graph this quadratic. So first I find my vertex. Because it's an x minus 3, I know that shifts it 3 to the right, so that makes my x value 3. And because it's a plus 6 on the end, it shifts it 6 up. So the vertex is at the point 3, 6. So I go over 3, up 6, and I plot my first point. Now I need to find extra points. My a in this case is negative 1/2. So what we've been doing so far is my next 2 points, I do a times 1 squared, which is negative 1/2 times 1 squared is 1. I get negative 1/2, which means I go over 1, technically down because it's negative 1/2. So from the vertex, over 1, down half of a box in each direction. And then for my next 2 points, which has typically been my final 2 points, I do a times 2 squared, which is negative 1/2 times 2 squared is 4. I get negative 2, which means I go over 2, down 2. So I go over 2, down 2, over 2, down 2. Now, if I was just asking you to graph this, this would be sufficient and I would draw my parabola between it, or around it, through it. Having said that, the problem is I need to know exactly when this parabola crosses this line. So if I draw a sketch right now, I wouldn't be as accurate as I need to be. So I do need to continue to find points on this parabola until it actually hits that line. And so the strategy we've been using is a times 1 squared, a times 2 squared. The 1 and the 2 tell me how far over from the vertex I go, and then the answer tells me how far up or down I go. The only reason we've been using 1 and 2 is because it's the closest points to the parabola, and it's going to be the easiest math. Having said that, nothing stops us from finding more points by doing a times 3 squared. This would mean go over 3 from the vertex. So I'd have negative 1/2 is my a, 3 squared is 9, I get negative 9/2, which is the same as negative 4.5. So I'm going to go over 3, down 4.5 boxes. So 1, 2, 3, down 1, 2, 3, 4.5, over 3, down 4.5. And you can see that's still not enough. I still have a nicer picture, but it's not on the blue line yet. So I keep going, and I would do a times 4 squared, which means from the vertex, I go over 4, negative 1/2, 4 squared is 16, I get negative 8. So if I go over 4, I should be going down 8 from the vertex. So from the vertex, 1, 2, 3, 4, down that's 7, and 6, 7, 8. Over 4, down 8. So you can see that those points, when I go over 4, down 8, do in fact land exactly on that line, which is the line we care about. So in this case, I actually had to go all the way up to a times 4 squared to make sure I found these exact points. So my two ordered pairs of intersection are negative 1, negative 2, and 7, negative 2. But remember, for our final answer, we just want the x value. So x equals negative 1. Because there's two answers, I use or. X equals 7. So x equals negative 1 or x equals 7. So this is a good example to show us that sometimes we do have to keep going further when we're graphing those parabolas. Alright, so now that we reviewed solving graphically, now we're going to switch gears and talk about solving algebraically. Now again, the steps we follow are going to be the exact same as the steps we followed with solving absolute values. Except instead of isolating the absolute value, we're going to isolate the squared part of the expression. Which means I'm going to isolate the x plus 1 squared in this case. So first I would subtract my 3. I get negative x plus 1 squared equals negative 16. I have this negative out front, it's like a negative 1, so I divide both sides by a negative 1, and I get x plus 1 squared equals positive 16. So the squared part is by itself. So now I go on to step 2, which is I need to decide if it can be solved. And the rule is the exact same as absolute values, and that is if I have the squared part by itself, it's critical that it's by itself, it has to be equal to a positive number, which it is in this case. And the reason that's important is because if I have a square by itself, anything that x plus 1 is, if x plus 1 ended up being a negative number, I would take that negative and square it, which makes it positive. So I can't take a number and square it and end up with a negative number. That's why we end up with this. Okay, so my next step here, we actually learned this way back when. If I get to this point and I have an x plus 1 squared, the way I get rid of the square is I take the square root. So I get x plus 1, and again, that's what it was before I squared it. And so for kind of the same reason, with absolute values, the x plus 1 before I squared it could have been positive, but it also could have been negative. So the reason that's important is because when I square root both sides, I could have ended up with a positive 4 as an answer, but I also could have ended up with a negative 4. So this is another case where when you square root both sides, you're going to get two mini equations you need to solve. X plus 1 could have been positive 4, or x plus 1 could have been negative 4 before I squared it. So I would subtract 1 from both sides. I get x equals 3. Subtract 1. X equals negative 5. And again, because I have two answers, I'm going to put or between them. It could be one or the other. Alright, last example on this side. I have my squared, so I need to do step 1 and get the square by itself. I subtract 5 from both sides. 3 times x plus 4 squared equals -3. And divide by 3. I get x plus 4 squared equals -1. And this is where we want to be careful. Step 2 is decide whether you can solve. And I have my radical by itself, and I say, oop, can't equal, I have a square by itself, and I could never square something and get a negative answer. Now, if you accidentally kept going, the other way you would realize in this case that you can't do anything is your next step would be to square root both sides, and you would see I can't take a square root of a negative. So that would be a visual for you to be able to understand that there is, in fact, no solution. So again, this video introduced the 2 concepts you need to be able to do from section 8.6, which is being able to solve quadratic equations, both graphically and algebraically. And now you will pause this video and go to the next one where we'll look at the backside, and we'll have you solve both algebraically and graphically for 4 more problems. I do encourage you, if you feel pretty good about what you're doing, you could do this before watching the next video. I'll walk through number 1 first kind of thoroughly, and then I'll give you the answers for 2, 3, and 4, and then walk back through them. Thanks a lot, and keep working hard.